we'll get started. Okay, so I'm going to go ahead and do a recap. So today we're going to talk about Kaplan-Meier, or time to event, which is a really important concept in outcomes research. But before that, we want to do our recap. So the database is a regulatory database, so it is very good in certain respects. Things like survival and the fact that a transplant did happen, it's very good. It's because it's based on regulation, and programs have to submit data every 6 months, so the programs can be viable and have clinical license to conduct transplants. So that's the basis of this database. It really started in the mid 80s, like 87, 86, 87, and of course it is updated every 6 months. So that's the database that we're using. There's about 300 variables in the liver database. There's about we saw about 300,000 people listed in the modern era. So if we, the first thing that we want to do is with our code, going in the code, is inclusion, exclusion. Exclusion, exclusion is very important. And what we basically do is we put our exclusions and we're left with our inclusion, our study cohort, which should be somewhat homogeneous and contemporaneous and homogeneous as much as possible to do an analysis. When we do our drops, we drop if the transplant date is blank, because this is a database that has people listed and as well as listed and transplanted. So there are people who are listed but not transplanted, of course. So we want to exclude those. We want to look at just adults. So I'm looking at the age of under 18 to drop. The modern era we discussed, March 2002 is when MELD allocation came into effect. Patient status is a very important, PX stat is a very important variable. It tells us the follow-up, the status, the last known follow-up. And if that isn't there, we want to drop that. We want to drop if there's live donation, because there's two types of transplants. There's brain dead donors or cadaveric donors and live donors, and they're apples and oranges. So we want to focus, again, for the sake of making a population homogeneous, on just cadaverics, and we're going to remove all of the combined transplants. So we'll go ahead and cut and paste that. We do want to make mention of the double negative, not equal to blank, which is a double negative. And the reason we are doing that is because we assume that entry completion will be done if it happened, because it's a very significant event, but a rare and significant event. Okay, so we go ahead and made our drops, and we look at our patient code. It's 83,000 patients, and you guys hopefully are coding at the same time, right? And so let's get to that point of coding. So everyone has got 83,000. Again, part of this is repetition. If you guys can raise your hands if you got 83,000 up there. Good. Okay, good. Okay, so next, after we did that, we wanted to talk about building variables, and the fact that the actual stock variables and building variables is the art of this analysis. Any analysis, it's the most important part of it. And so there has to be a lot of time spent looking through the stock variables, as well as why we make our own variables, so that we understand the variables and everything's a 0 and a 1 for analysis, okay? So we talked about a couple different aspects of looking at variables. One thing was to always look at the data browser, to look at the data in its raw form, also to look at the legends, and to tabulate and summarize the data. We know from the code that categorical and continuous variables are treated differently, and they have different languages to it, and that comes out when we make our variables. So the first variable here we're making is ABO incompatible, and ABO incompatible, ABO compatible, and that's based on ABO mat. And we use quotes because these are categoricals, and then 1, 2, and 3 are found in the legends. And so we make this variable that defines, don't want to do logistics, sorry, that defines ABO compatible, but not identical, and ABO incompatible. Then we talked about making these bins or these categories of age. So we take a continuous variable like age and bin it into different categories. And we do that because it makes the greater power in each group because there's more patients. Also, it helps us to understand risk when we don't think it's linear. When we think it's going to be more extreme on the, it's going to be more risk at the extremes. Making these variables takes a lot of clinical experience, and so a lot of these things are done with respect to the clinical relevance. And so, for example, here when we make our groups of age, of recipient age, it's much less granular than the donor age because donor age is much more impactful, more significant. So that's why we do that, and there's a reason for these things. And when you make your groups, you do not want to overlap. Everything has to be distinct. So we have to use greater than equal to and equal to very carefully. And everything should be a 0 or a 1. Okay. And so here we go. We build this age here. One second. Yeah, so here we go. We built this group, these groups of recipient age, and we want to check them, these variables, and we can check each one, see everything's a 0 or a 1, and we can also make sure that there's no overlap, and there should not be any overlap. And we see that for 1 and 1, there's no overlap, which is good. Okay, so we did all that. We talked about the reference group, right? And the reference group is the one that you don't code. You code for every risk factor, and you don't leave the reference group uncoded. And so we did that with age, and we see the age here in the middle is a reference group between 30 and 60. And we also showed you examples where the reference group is in the beginning of the scale, at the end of the scale, like albumin, for example, and BMI, for example. Okay. And we want you to go through and make all these variables and understand all these variables. And that can't be taught. That's just you guys going through it, and it's a bit tedious. But that, again, is the most important aspect of understanding a database. There's no question. Okay, so now we're ready to go on to Kaplan-Meier, which is the new part. I just finished the recap. Does anyone have any questions up to this point? No, everyone's good? Okay, so let's talk about Kaplan-Meier. Kaplan-Meier is one of the fundamental building blocks of outcomes research. Have you guys read about Kaplan-Meier? I'm sure you've heard about it, but in your medical school, have you read about it or do you know it? Maybe you guys have some background, but I'm going to go over it once again. And basically what it is it's time to event. I'm going to put some code up here, so I'm going to get an example of a Kaplan-Meier, and then we'll discuss it. You don't have to understand the code right now. Actually, I want to do something better. Okay, so what a Kaplan-Meier does is it's looking at the entire experience of 80,000 patients that we've transplanted. And it wants to put them all at the beginning as if they were all transplanted on the same day. So you guys can see my arrow, right? Everyone can see that? So we want to assume, and we want to, for this equation analysis, because people, these 80,000 transplants are transplanted over 20 years, and they're transplanted all throughout this 20-year time span. But what we want to do to look at the data in one coherent view is we want to assume or make the assumption that everyone was transplanted on the same day, day 0. Okay? So you put everyone transplant on the same day, and you show how the survival falls off with time. But everyone needs to get credit for the amount of time that they're in the study, and they need to have an outcome. They need to be either alive or dead. So this is why Kaplan-Meier is called time to event analysis. Every patient has a time and they have an event. The event is death in our case. So everyone has a time and they have an event with respect to death, either alive or dead. So what that allows us to do is it allows us to take people with different amounts of follow-up time and put them on this graph. So someone who was transplanted in 2019 has 1 year of follow-up time. They're still alive, but the 1 year of follow-up time. And you have someone transplanted in 2003 who has 20 years of follow-up time and is alive. So each one gets their own credit. And it may take a little bit of time to wrap your mind around it. It's not even, and it's a little bit more complicated than it appears, but we have to think about it. And I'm trying to do a good job of explaining it, but oftentimes I find it difficult to explain properly. But I'll give you an example. So we start off with roughly 80,000 patients, and this is the number of people at risk. This line will drop every time someone dies, okay? When someone is lost to follow-up or they're alive, it doesn't drop, okay? If they're alive, it is part of, it is included. Oh, I gotta do a better job of explaining it. I thought I'd explain it better. I explain it better in person. I think that maybe Zoom. When I'm up on a blackboard, I can explain it a little bit better. But okay, let me try again. So everyone has a time and an event, and so what happens is that when you have less follow-up time, you have more patients in your study because everyone has had 1 month or 1 year of follow-up. Majority of people have 1 year or 1 month of follow-up. But 15 years of follow-up, very few people have actually had that. To have 15 years of follow-up, you had to be transplanted in 2003, 2000 to 2005 to have that much follow-up. So the number of patients in the study goes down because one, that they die, and two, they don't have the follow-up. And so what happens is a patient is alive, and with a certain amount of follow-up, he's included to that point. And if he's still alive, he's part of that study. But as soon as he passes the follow-up period, he's not part of the study anymore. Does that make sense? I know it's a little bit hard to understand, but the whole point of this is it takes a real life situation where you transplant people in a 20-year course at all different times. And you want to be able to look at that data coherently as one. And the way you do it is you move everyone to time zero, and that's 100%. And as it goes down, as you progress with time, there's less and less people within your study. But it's not because they died, it's because they don't have the follow-up. So death is only what is going to cause this number to drop. That's real death dropping. If you run, yes, Tahar.
So how does the curve account for patients who are lost to follow-up? Does it drop at all, or do they just sort of?
So those are censored. Okay, if you're lost to follow-up, you're censored, which means, which is very similar to being at the end of follow-up, where they're just not included in the study further on. So you have 2 years, and then you're lost to follow-up. You get 2 years of life credit, but after that 2 years, you just dropped, right?
So it's almost like if you had 10 patients, and if we go out, it looks like 15 years, right? Mm-hmm. Then if one of those patients drops at 5 years, the curve, instead of calculating out of 10 patients, it'll calculate out of 9 patients.
Right.
5 years dead, right?
Right. At every time point, it resets.
Yeah.
At every time point, it resets. But the only thing that's going to cause this to drop is death. Okay? death is going to cause it to drop. So, and by the nature of Kaplan-Meier, you have a lot of patients in the beginning, and it goes down over time. Every Kaplan-Meier does that. Because, you know, if you're looking at 20-year time span, everyone's got 1 month. Almost everyone's got 1 month of follow-up. So at that point, it's like really good. And most people are alive at 1 month. Okay? So spend a little time understanding this. Understand that the number at risk goes down over time. And this is the bedrock. These are the survival curves that we have and we publish. It's the gold standard for looking at survival in a real life setting. Like if we were doing an experiment, we said, okay, well, what's the the survival of someone of transplant, of liver transplant, and if we were doing an absolute experiment, we would do all of them at the same day and then follow them, right? But that's not real life. Real life experience, people are being transplanted at various times throughout the 20-year time span. And so you want to give credit. So everyone, no matter how, even if they're got transplanted and they're alive for a month and then they're lost follow-up, everyone gets credit. You get credit for one month of life. Okay? Does that make sense? It's hard to understand. So
I have a question.
Yes.
So I guess just to maybe recap. So counting for death is inherent to Kaplan-Meier. It's not like some other thing you have to code for. It's just part of the function.
No, you have to define your outcome.
As like an input to that function?
Yes, we'll define. Okay. You could define your outcome as anything. And we make curves for transplant, getting transplanted, for anything. You can make anything. But your outcome is you define. And that's part of the code. We're going to go over that in about 5 minutes, actually defining your event. But it could be anything. Like we've done a prolonged length of stay. We've done many things and made Kaplan-Meier curves on. But it could be any event. But generally, and for the simplicity of trying to understand Kaplan-Meier, you should just think of it in terms of death as a survival code. Okay? Okay. Anyone else? Any other questions? No? Everyone is okay? So time to event, it's a time to event analysis, and that's a Kaplan-Meier. This is the entire experience of liver transplant in the United States, 80,000, the entire experience. So you can see at 10 years, you have about a 60% survival. Okay. So, and you can grasp that from this analysis. So let's talk about.
Out of curiosity,
yes.
Excuse me. I was just curious whether the drop off at the very end of that curve was related to sort of the outer limits of how long a liver transplant lasts, or is that an analytical quirk that it drops pretty steeply?
Yeah, that is an analytical drop because, and we see this at the end. There's so few patients here that it throws off the entire analysis. You don't see this generally. It really is a smooth projection. See, it goes straight, and this is really just there's no more people there, and these graphs generate. So what we'll do is sometimes we would cut this tail off at 15 because it's just noise. Okay. What we would
cool.
expect,
thank you.
Yeah, we would expect a normal line, right? That if you just graphed it out, okay? Okay. Okay. Anyone else? No? Okay. So let's go through the code. So like I said, the key to understanding this is time and event. So the first thing we want to do is we want to define our event, which is death. And as I mentioned, if we look at patient stat, that is our key thing. Now there's also, Tahir, you may want to look at this also. There's also something called P status, which looks at, it's a composite death date, which we should be using, I think, in the future, Tahir, and is because P status, it looks at linking to other sources, the death date, like Social Security death master files, various things. And you can see that it's very similar. It's 22,000, 23, but it's a little bit better. So we should start to, and this is only in the newer databases. So we should start to really focus on using P status instead of PXStat. So I'm going to change it actually. This is the first time I'm going to change this to P status.
I think in the past, I've used like G status before, and I mean,
G status was always there, but P status wasn't.
P status wasn't okay.
Yeah. Okay, so I'm going to generate failure is equal, P status is equal to 1. Now, P status is death. Now, I already defined failure before because I ran that code to generate the Kaplan-Meier curve. So I'm going to drop failure, and then I'm going to generate failure. And then there you go. You get zeros and ones and 23,000 deaths. That is death. 1 is death, 0 is alive. That's the event. Now the time, luckily, there's a time for everybody in this database, and it's called P time, which is patient survival time. And it is basically the amount of time they're under follow-up in the study. So they could be alive, lost to follow-up, they could be alive with follow-up, they could be dead, right? But everyone has amount of time that they're in the database. And so that is conveniently coded as P time. Okay, and what I want to do though is I want to change this into P years because it's just easier to do. You know, that's how we look at Kaplan-Meiers. We don't, and I already defined it as well, but it's already defined, but I could. Okay, so now we actually generate our Kaplan-Meier curve, our Kaplan-Meier analysis. It puts everything into a Kaplan-Meier analysis. And the keys are 2 things, time and event. Time is here, and this is the language, ST set is putting the data into a Kaplan-Meier analysis. Failure is your event, and we define failure as death, but we could have changed this to death. And you know, for the simplicity's sake, I'm going to change this to death so that it's easier to follow. So I'm going to go ahead and generate death is equal to 1. And code is like 1 letters off. It's not going to work, right? I wonder if anyone computer coded at all? Has anyone computer coded? You guys have? I'm sure that no, you haven't, but some have. It's not, you know, it's similar thinking is there. You know, you have to check your code. One thing is wrong, the whole analysis is off. Okay, so I'm gonna just put my time there, and so I'm gonna change this to death, so it makes it a little bit simpler to follow. So failure is death is equal to 1. Okay. I have the time, event. The last thing is a unique identifier because every patient should only be counted once. So you need some sort of unique identifier. And so here we go. And now it puts into a Kaplan-Meier analysis. And these are the total number of observations. It tells you the number of failures. It tells you the number of time at risk, which is really important. So that's the number of patients times the number of years, and that's the time at risk. So now it's in Kaplan-Meier, and all you have to do then is write STS graph, and you actually produce your Kaplan-Meier curve. Boom, right there. Okay, can you guys do that? I want you to create your own Kaplan-Meier curve, and then raise your hands when it's up. Okay, good. That's everyone. So Kaplan-Meier, time to event. The next thing I'm going to teach you is regression, and that's really all there is, right? It's variables, it's Kaplan-Meier, and it's regression. And then boom, that's the bedrock. And then you could go. Now we have a lot of other stuff to go over, and there's some practical things and stuff. And I'm going to have so we learn about 2 types of regression. we learn about logistic, and we learn about Cox regression, 2 types of regression. But there are many types of regression. And I think I'm going to have the statistician. We have a statistician associated with this course who will give, I think, Tara, that would be a great one to do. Well, let's email Carly and ask her. I think that would be the different types of regression that's out there. Okay? For a guest lecture.
Yeah.
But I'm going to get into regression now. So regression is basically looking to see if one thing is associated with another thing and what the degree of association is. In our case with the soft score, it's very simple. Risk factors, what's their association with death at 90 days? So regression basically assumes that there is a linear relationship and it gives a slope to that relationship, to that line. And it is not the same thing as causation, right? This is the old adage, right? The difference between causation and association. Association is all we find out from regression. It tells you one thing is associated with another thing. To prove causation, you have to make a case, either circumstantial evidence or you have to show mechanistic evidence that there is causation. But here, all we're talking about is an association. We're saying one thing is associated with another thing. A great example is, what's a great example? Ice cream in summer, right? Is that right? You guys heard that? Ice cream in summer, right? Is that right? What's a classic association causation example? Does anyone know of one that can explain? There was an ice cream in summer. I just can't remember the details.
Yeah, so I think the causation or correlation with that is just that, like, kids buy more ice cream during the summer, and then it's like, oh, is the cause of, are they buying more ice cream because it's that time of year, or is it because it's hot or something like that? And I mean, yeah. I mean, I think everyone. I mean, do you guys understand like what we're talking about in terms of correlation versus causation? Just because things show up as correlated doesn't mean that one might have caused the other. Right? Okay.
Yeah. A great example. I'll give you an example of this. So you find out that drinking alcohol is associated with lung cancer, right? And they're associated. They're linked. They go together. The more people who drink, the more lung cancer you find, right? But it turns out that it's not, and that's a true statement. But it's not because the drinking causes the lung cancer. It's because the drinking is linked to smoking, and heavy drinkers are more likely to smoke. And so the smoking is actually the thing that causes the lung cancer, but the alcohol is linked with it. And so if you look at just alcohol and lung cancer, you see there's an association, but not a causation. Okay, so that's the idea. But regression, and here all we're looking is there's no mechanistic studies in any of this stuff. This stuff is all association. We're saying one thing is associated with another thing. And the simplest thing that we're going to learn is logistic regression. And that's what the soft score was based on. It's 90 days, and 90 days is a patient alive or dead. And we're looking at death at 90 days and whether certain risk factors are associated with that. Does that make sense? Okay. So what we do is we are going to define our outcome. In regression, there's also an outcome. We call it an independent value and a dependent value. So the independent one is we're assuming is the outcome, and the dependent one is independent ones we assume are the risk factors, and the dependent one we assume is the outcome. So, but to make it simple, it is death at 90 days. So let's actually code for death at 90 days. So we're going to say here fail. Okay. Now I'm going to change this from pxstat to pstatus because I think we should start using pstatus. It's a little bit tricky because in some databases it's still pxstat, like the lung database and the heart database, but they have the p status in the new kidney and liver, and I think it should be used instead. So we're going to say generate fail is equal to 1, and p status is equal to 1, and p time is less than 90. So that's death in 90 days. And you may want to ask, well, why did we define death in 90 days? Why didn't we just say death? Well, it turns out to predict death 10 years after transplant is really hard. But to predict death 90 days after transplant is not so hard. Okay, because if they get past the first year, they're not going to be dying from complications of the operation. They're going to be dying from heart disease, cancer, and you can't predict that stuff. So for the soft score, it was a realistic goal to try to predict death early. And so that's why we chose 90 days. So we defined our outcome here of death within 90 days. Now, logistic regression is one thing associated with another thing. There's no time in it. It's just yes or no. So we make the time. So if you die within 1 day or you die within 89 days, it's the same thing. You're dead within 90 days. That is clean-cut, binary logistic regression. And so we created these variables, right? We created ABO compatible, all these variables. All we have to do is write logistic fail and those variables. Logistic fail variable. And this is going to give us an odds ratio. And what this means is that ABO incompatible is associated with death at a 40% increase risk of death within 90 days compared to the reference group. So that's what this odds ratio means. The 1.40 means 40% increased death. This risk factor causes 40% increase of death at 90 days. You look for the p-value to make sure it's significant. It's less than 0.05. And the confidence interval here should not include 1.0. It should be greater than 1.0. And so that's a simple concept too, but it's a profound concept because now we went from defining the variable of ABO incompatible to actually giving you a quantifiable risk of this risk factor. So it's so simple, but it's pretty powerful and pretty cool. And that is the basis of things like the Framingham risk score. All concepts of risk and outcomes analysis is based on this regression. Okay? The next one is ABO compatible but not identical, 1.7. So this would be 70% increased risk. Okay, let's stop here. Does anyone have any questions? Do you understand? Regression. Hands up if you understand. Okay. Okay. All right. Well, I'm going to ask you each one individually just to, because we have so few people here, we can do that. So Malcolm, what do you think? It makes sense to you? Have you heard about regression before?
Yeah, I've had some exposure to it, and I think this makes sense, especially given once we clarified, like the end is 90 days death, like that's what we're, the event we're looking at.
Yeah, Cox regression is logistic regression is very clean, 0 or 1s. And Tahir, you've been doing this, you know this. And then Carolyn.
Yeah, it all makes a lot of sense. I've done some work.
Caroline or Carolyn? Caroline.
Caroline, but I answered both.
Okay, fair enough. So you've read about it, you understand it, all that stuff.
Yeah,
okay.
It's great.
Adrish? And am I pronouncing your name right? Is it Adrish?
Yeah. Mm-hmm.
Okay.
Yeah, I've had like some past exposure to it, so it's not totally new. So.
Okay, but it's remarkable that this is really like the bulk of what outcomes work is. It's Kaplan-Meier event, time to event, and regression. And the database aspect is understanding the variables. And it takes time to do those, to understand the variables, but nothing else takes time. Everything else is pretty easy. Okay, so now this is called univariate regression. One thing associated with another thing. But then what happens if you have multiple factors and you want to look at what the independent risk of those factors are? Like, for example, let's say I'm obese, I smoke, and I have diabetes, right? All three of those things are going to exert increased likelihood of dying. But what we want to do is we want to say, well, what if we adjust for the others? What does each one independently, how is each one independently associated with those things? Because, if you're obese, you're likely to be diabetic. They're linked, right? They tend to go together. So where do you know, what is diabetes and what is the obesity? If you have enough patients, you have enough patients where you have enough people who are diabetics without being obese, and enough people who are obese without having diabetes, that you can tease all of that out. And so that's what a multivariate is. A univariate is one factor, death. Multivariate is you put a bunch of factors in, okay? And each one independent, and you put them all in a pot, and you say each one has an independent effect adjusting for the other ones. And what is that effect? And that is what a multivariate is. And that's how you generate a soft score or any kind of score, is a multivariate or multivariable analysis. Okay, so the first thing is you can't just put anything into the pot. You have to have some methodology to actually going from univariate to multivariate. The gold standard is if it's significant in univariate, then you add it to multivariate. If there's a significant association with a one-on-one relationship, then you put it into a multivariate. And that is the gold standard classic way of doing a Kaplan-Meier multivariable analysis. And so here we actually ran ABOI, and we see both of these things are significant. And so I bolded them. That's why they're bolded, because I'm going to later add them to a multivariate. And here we go age. We made these groups, remember? And so now, and I'm going to run this logistic regression, and it turns out age 30 is not significant. See, the p-value is 0.8, and the confidence interval includes 1.6, so it's not significant, and it's not bolded, right? Age 65 is. This shows you that we say age 60 to 65 has an 8% increased risk, and it is. Has a p-value less than 0.5 and confidence, so it is significant. And over 65 is 27% and significant. So both of those are bolded. But that's a one-on-one. That doesn't really mean anything, right? You want to see what being over 65 is, what kind of risk it is when you adjust for every other known risk factor. That will tell you really what being over 65 means in terms of death. And you can see now you understand the code, right? All these missing pieces. And that's why I created variables, and then I run the univariate. And then I bolded them so they'll be included later on in a multivariate. And so you just go and you could do all of them. And then boom, donor age, and all of these things come out. And you get every one of these risk factors. I'm looking at what risk for death in 90 days. A donor over 70 has a 20% increased chance of dying within 90 days. Those are bolded, okay? Albumin. Now see, albumin's interesting. It's significant now, but it doesn't pan out in the multivariate. Okay, so anyways, you guys get the idea, and that's the power of this code. You just copy and paste this all. And it's bolded, and those are the ones that are significant, the ones that are bolded. Now you understand the power of the variable, right? Look at all of these variables. That is the art of this. Binning them, making them categories appropriately, choosing the right ones, making sure that they're accurate, that there's enough of them. The entry completion rate is correct. So all those things are there, and it's complicated. But that is what it takes to do this. I mean, that's where the art is in making these variables, but all of them are done. And so generally I find that's why, and Tara, you could do, that's why people are able to turn papers out. Right, Tara? Because the variables are made and coded, and I tell you which variables to use. And that is the most effort intensive stuff there is. And then the analysis comes out okay. But if you guys go on to different databases, there is that learning curve of learning the data and learning the variables and which variables you can use and how do you categorize it and all that stuff. So anyways, we ran this whole thing. I don't know, my computer is getting slow. It's quite slow for a database this size. I think I need to get a new one. Maybe it's too much memory use, but usually it goes faster. Okay, so now this right here is going to be, I'm going to highlight it, is my multivariate, right? Which is, I mean, it's like utterly simple. You know, it's like making Rice Krispie treats or something. It's like logistic fail, all the different variables that were significant in univariate, right? That's it. It's a big list, as you guys can see, you know? And so let's interpret this. So now we have ABO-I, ABO compatible, and ABO compatible, which were both significant in univariate, are not significant in multivariate. So that shows you that they were linked to other things, and you know, sometimes it may not be true. Like reality is different from what the numbers show, right? The numbers show associations. And so you have to view it in the view that these are what these are what the analysis show in terms of associations with numbers. And then how you interpret it is different. How you interpret it is the case that you make. But the numbers are the numbers. And so this is just showing us what the numbers show in terms of association of one risk factor for the other, adjusting for the others. The mathematical equation has nothing to do with clinical relevance. Does ABO incompatible affect death? Absolutely, if you ask me. But it's just not done enough. It's such a rare event that you can't see it. It doesn't come up in this analysis. It gets lost in the other variables. Because when you do an ABO-I, an incompatible liver transplant, patients are deathly ill. I mean, you're kind of throwing you in a desperate situation. So it's hard to tell what are they just sick, or is it, you know, and you don't do very many of them, so it doesn't come out. So I think ABO-I is a great example where I'm sure it has an impact on death, but it's not going to show out in the analysis, and that's just the analysis. Now, age is 65. Now, 33% increase if you're above 60 to 65, and over 65, 55% increase. That was different from the univariate. You can see like the univariate and the, you know, but that's the way it is. I mean, this is a multivariable adjusted analysis. Now, if you don't have many patients, you have to be very cognizant of the number of variables that you use. You can't, it won't support, if you have 200 patients, it will only support, I think 200 patients, I don't know, there's ways of calculating this, but 200 patients are going to really, you know, allow you to do probably 4 or 5 variables. But when you have 80,000, you could do anything, right? That's the power of databases. You could do I could run anything. I have enough patients to justify this. See, donor age, when they're young, this is a protective thing, right? Because it's not included 1.0, it's below 1.0. And this, what does this correspond to? This is a 35% decrease risk of dying within 90 days when the donor age is young. And donor age that's old these are risk factors. Being obese, 11 and 18%. Cold ischemia time, DCD donors, MELD score. So it's all there. Does anyone have any questions to this? This is multivariate. Any questions?
So we have a lot of variables here, and is there a way for us to automate and generate a list that only displays the significant ones? So could you have like a loop or something that determines is the p-value less than 0.05? So if I'm like understanding this correctly, you can manually go through and pick out all of the ones that you find significant, but that seems a little tedious.
Yeah. That's something that I tried when I was doing my project with Dr. Rana. It's like Stata is nice because it does like the analysis like this, but there is probably a way those variables are stored somewhere. That table is stored somewhere. The trick is just figuring out how to just pull that table and like make that list of variables with the arrays and everything else. Stata is you got to learn the language, and I mean, I'm still learning myself, and that's not something I figured out yet. But I had the same thought, and something I'm trying to figure out too. So maybe we can figure it out together.
Yeah, I don't know of a way, but you know what? But it doesn't take long, you know, to pick out the variables. I'll tell you the way I usually do it. I just go copy table, and I go to an Excel sheet, and then I just go right here, delete row, right? And then I just hit a Control Y when it's not significant, and then it can literally. Oh, it didn't work. And then I'll just go through these, and you know it'll take me 3 minutes to cut out the ones. But yeah, I don't know of a way, but the multivariate is going to generate all their variables, and it's going to give a value for all of them. So that, from experience, that's not the tedious part of it. You know, it takes like maybe a minute to do that when you get fast with the Excel and stuff, cut and pasting. The other things are tedious, and there are ways. Now there is a shortcut called backward stepwise elimination, where you don't have to do and manually go through each one and do univariate, and you put them all, and what it does is it drops the least significant one. It keeps dropping the least significant one until you get to you actually get to all significant values. So that is that in some ways may be. Let me see if I could show that. I just don't really remember the code. Let me see. Yeah, I need to organize this code. There's no doubt about that, and I will these days. Where did I see that? I just saw that recently. Tar, what were we doing? Marshall Healthy's had it. That's where it was.
Oh, is it in the marginal? Okay.
Yeah, that's where it was. Let's see. I bet it was here. No. Okay, anyhow, I'm going to prepare for the next lecture with multiple imputation and stepwise backward stepwise. Okay, so we'll do backward stepwise and multiple imputation. So I'll go over that in the next lecture. Now, the next part of the soft score was actually assigning risk to each risk points to each risk factor. And so it was very simply done that if a risk factor, for every 10% increase in risk, there was 1 point awarded. So for example, if in the original soft score, for this risk factor, this would be given 6 points, because 5.5, but you round to 6 points. And that's all you do. You assign everyone a risk factor of a certain number of points. Now for this class, what I did was for every percent, I added a point. So I'm generating here a score. And for example, so 65 is 34 points, right? 33.8, 34 points. So you say generate A, and I'm making dummy variables. I say A is equal to 34 if age 65 is equal to 1. That means if a patient has this variable where age 65 is equal to 1, that means they're between 60 and 65, they're given 34 points. And I just go through all the variables like that. And so basically, you're assigning a point total for every variable based on this, based on every percentage point, and then you add them together. And so then that gives you the soft score, basically. Yeah, it's incredibly slow. So, okay, And so now I'll just tabulate it. So now, see, these people have negative points because there are negative points, right? Because if, for example, we said donor age here would be negative 34 points, right? Because it's 34% decrease. And then here you see donor age 1 is equal to negative 34. So there's negative or protective points in the soft score. And these patients had a lot of protected points. And then you go to the end and you have all the different point totals. And these are the number of patients with those point totals. So every patient can have a variety of risk factors, right? You have multiple ones. And you take every risk factor is given a weight, a score, and then for each patient, you add it up. So every patient has a score here. And this is the distribution of that score. And then what you could do is you can make groups, okay? Let's say we'll do one in real time, and we'll show you this Kaplan-Meier curve. Let's go. We'll make two groups. We'll make less than 10 percentile. So this is the percentile, so under 40 points. So we'll say generate group A is equal to 1 if supply, that was the name of the score that I made, is less than or equal to negative 47. And if we go and we want to look at the other side, the greatest 10%, so we go to the 90th percentile. This is the 90th percentile, 109, right? So we'll say generate group B is equal to 1, or I'm going to say 2 actually, because I want them distinct. If supply is greater than or equal to 109. Okay, so then I recode group A, group B, blank is equal to 0, because everything has to be a 0, 1. Now, if I go to tab group A, see it's about 10%, right? This is the 10 percentile, the best 10 percentile based on the score that I just made. And this is the worst 10 percentile, okay? And then, so then I'm gonna say generate group is equal to group A plus group B. And here you got 1, which is the best 10%, right? 2, I'm sorry, yeah, 1 is the best 10%, 2 is the worst 10%, and 0 is everybody else, right? And then so I'm going to go STS graph by group, and then you're going to see how good our score is. That's our score we just made, right? This is the worst group, their survival, best group, and then everyone else based on the percentile. So we did that real time. And that was the soft score. I mean, that's all the soft score was, right? And that soft score's got like 300 citations already. It just shows you the power of just simple associations. Now, we do want to generate the C statistic. The C statistic is important because the C statistic, do you guys know what a C statistic is? So I'm just going to, this is like interesting way, you know, of doing anything. It's just on Zoom is like a different way of teaching. I can just pull up graphs of C statistics. Okay, that's not the right way to look at it. So you go area. This is it right here. Okay, so this is the C statistic, and right here, this is what you classically learn it as. Sensitivity, 1 minus specificity, and you graph for every one how it correlates with what you expect to what is observed. And basically it tells you how good your test is. Flipping a coin has a 0.5 C statistic. Perfect model has a 1.0, okay? Another way of looking at it is this, where you have the true positive and your false positive. Okay, and then the area under the curve is the thing. You need to wrap your mind around it, yes, but essentially it's a grade of how good our model is. 0.5 is worthless. 1 is perfect. MELD, for example, the MELD score has a 0.8, and that was considered to be revolutionary. 0.8. A 0.8 in a real life model is great, and 0.8 is like it's usable. 0.7 is good but not usable. So we just write this simple code, rock tab fail supply. And there's a 0.7 C statistic. Which is what it was. So it becomes good, but it's not used clinically because it's not good enough. You need about 0.8. And so this is the area under the receiver operating curve. These are all my patients and how they did in terms of, true positive and what is it? True positive, false positive?
Yeah, true positive rate is the y-axis, and then false positive rate is the x-axis.
Exactly.
So
that's it. But this is good enough. 0.7 is good enough to publish. I'll tell you that much. So, and it's good enough for a lot of things. But 0.8 is the goal. 0.7 is good enough. 0.8 is the goal. So that's all it is. I mean, we basically learned you could do the soft score with a little bit of practice. Everything we did was we're done with every line of code. You should understand here. Any questions, guys?
What I'll say is you guys need to know what the C-stat is for your step 1. Is it pass-fail for you guys? I don't know. You guys might be the pass-fail class.
What step 1 is pass-fail?
Step 1 is about to become pass-fail, Dr. Anna.
Wow. So then you guys really need research if it's going to come.
Yeah. I mean, I think
what else is there?
Step 2 CK. I think CK will be the next marker. Everyone's gonna you're gonna see these step 2 CK scores skyrocket. Not my year, but the year after or the year after that, where these guys are. But there is a small little paragraph on receiver operating curves in your first aid book. It's not that helpful. I think with Dr. Anna, just the way he taught it is a lot more useful and makes a lot. Does it make sense to you guys though? And yeah, Dr. Anna's right. Basically, I did the same thing for the risk index that I made, and generated the same thing and got a C-stat of 0.8. We submitted that to a journal and we're just waiting to hear back from them. So I will add that.
Okay, now there's 2 lectures that are really good at this stage. And one is Teddy Zhang and Brent Price are both STAR students. And Teddy Zhang's from idea to publication, and Brent about how to publish. So those are 2 good lectures to watch. I think that we should maybe watch it. I don't know. What do you think, Tyler? Should we watch it within the class context? Or hey, Tyler, are you recording this by chance?
This is recording.
Oh, thank God.
Yeah, no, I
always do this lecture over and over again.
Yeah, this is a complicated one, right? So,
yeah. Okay, awesome. I'm glad you were presence of mind that recorded. I didn't tell you to. Anyways, those 2 are good lectures. I think we may put them in a class and then discuss them afterwards. Okay, but you want to get a preview. Those are pretty good. So what we're going to do now is we have a couple. We're going to have one more lecture on multiple imputation and on multiple imputation and on stepwise backward stepwise elimination. And then I'm going to talk about other advanced techniques by using Elizabeth's lecture. After that, we're going to actually assign projects. And then what we do is we take someone's project and we start to code the project and go through the project. And this is a great example. I did that with a class just yesterday. I did that with one of the students. So I'll give you an example. This is a class, because we did this class because of basically Corona, and we got credit for it and all, but I had run this class many times before, and this is one here. Let me show you, give you an example of this. All right, good. Okay. All right. Okay. So this, let me just fast forward it.
It's going to be interesting. This is going to be a recording within a recording. Dr.
I know that's going to happen because we're going to be playing these lectures.
But took the class.
Okay, so this is an example of a student who just Jordan just presented just finished a paper, and he just got done with the class. So I wanted him to give his experiences, but you could, all this stuff's online. Literally yesterday.
Yeah.
That's going to come up. Anyhow, we and you'll see it. You'll see is we take someone's project and we actually code it. So we're going to assign you guys projects, and we'll actually start coding your projects after these lectures, and it gives you guys a head start on doing it. So you guys could check it out. I don't think we have to wait for it to come through, but you could check that out, and then that's what is going to be on the schedule. So advanced statistics, one more, and then we'll start to we'll give you a couple of these like inspirational how-to lectures. We'll put them probably 2 into 1, and then we'll start actually coding projects. There's also a very interesting one that you guys might want to look at. Is I'm doing AI work with one of the students, Roland, and we've actually submitted some grants and wrote some papers on AI. This is, sorry, you should check this one out. Were you there for the AI lecture?
I wasn't there, but I'll watch that one.
Oh yeah, you should check it out. Super cool. We because like the soft score is a 0.7 C statistic, right?
Yeah.
With AI we get a 0.8.
Wait, that's awesome.
Yeah, and so we've already done it. We've submitted that paper to the Annals of Surgery. But anyways, Roland's getting a PhD in comp sci. He was a med student. He still will be a med student, but he's doing comp sci. So he gave that lecture. You check that out. I'm not going to put that in the course, but it's super cool. Okay, guys. Any other questions for now? Everyone's good?
All right. Should I go ahead and stop the recording?
Yeah.